himself gave to this wave. And what he did was essentially to write a classical wave equation for particle dynamics. And to quantize it, meaning when I say quantize it, if you know that you have one single particle, then the integral of this density over the entire volume of space should give you the mass of that particle. And if you have n particles, the integral of this mod squared of this density function over all space multiplied by some parameter which has units of which is basically that mu, that should be equated to n times the mass of each particle or the sum of the masses of all the particles. So that is where you are quantizing the wave when you explicitly put in this condition. What Schrodinger's equation is doing is it is by starting with the knowledge of how many particles there are. Okay. For example, if you have n particles in an ideal gas, you have a 6n dimensional phase space, you have 3n coordinates. The wave function now becomes a function of all 3n coordinates plus time in general. Now, the fact that you are using 3n coordinates means that the information about how many particles exist is already hardwired into this wave function, unlike the de Broglie wave function, which is a function of space and time. That's it. Physical space and time.
But why can we extend this de Broglie wave function to 3n dimensions like what Schrodinger did? Why it is
That is
necessary to
exactly
restrict in
then.
XY?
Then that is precisely what Schrodinger. That's what gives you the Schrodinger's equation.
Okay.
That's what gives you the Schrodinger's equation.
Yeah.
In addition to the realization that the operator, de Broglie did not define any operator for the momentum. All right. He only worked in terms of the wave functions. What the additional inputs that Schrodinger gave were that he defined these linear operators for the energy, for the momentum, etc., etc., and he worked in terms of those operators. So now the Heisenberg quantum condition of QP commutator equal to IH cross it became an operator identity where P is minus IH cross del by del Q for any Q. So that is how Schrodinger not only borrowed the formalism of de Broglie, he also saw a more fundamental aspect of that formalism which de Broglie missed out, which was the identification of these operators, which solved the entire problem, cast it into a fully linear problem. Now there is no problem with superposition of waves. All the eigenfunctions can add up and you can form a general state, which is a superposition of the basis eigenvectors, eigenfunctions, and linearity is preserved and quantization is taken care of. And you don't have to separately quantize the number of particles because that is hardwired into how many variables this wave function is a function of. All right.
Okay,
So
sir.
that,
So the first person come up with this wave function is de Broglie, right?
yes,
And how he
undoubtedly.
defined this wave function, or do he know anything about this?
Meaning
I mean, how he defined this wave function, de Broglie?
he just, so we did that derivation, right? He started with, let us say you have some wave function psi which
No, I mean,
satisfies.
does he interpret this wave function as a modern quantum mechanical way that we know
No,
today?
no, 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 no. We haven't actually. That is what we are going to discuss today. What is the interpretation of this wave function? Because de Broglie's wave function, as I said, is just a density. So this is the interpretation of de Broglie's wave function, right? This times the what you call mu integral over all volume would give you n times the mass of each particle. Let us say there are n particles.
Yes, yes, I understood. Yeah.
This is the interpretation of de Broglie's wave function. Now Schrodinger came up with a completely different wave function, which is, let us say, psi of no longer x, y, z, and t, but is actually x1 x2, so on up to xf and t, where f is the number of degrees of freedom. Yes, and as Sanjay pointed out, the interpretation for the Schrodinger wave function was given by Max Born, and we will discuss that today. Okay, so this is the Schrodinger wave function. It satisfies an equation which is completely linear. Now, in the last class, towards the end of it, I forget who asked me this question, but that was a very good question. So let me let me revise what exactly we. So let me just cleanly write down Schrodinger's equation. So there are two Schrodinger's equations that we encountered. One was simply h psi equal to E psi. This is the time independent Schrodinger's equation. And the solutions of this equation, or let me use more consistent notation from what I have been using so far. H phi equal to E phi, where phi are what we call the eigen solutions. Okay, or basis functions or basis vectors, etc., etc. Okay, then we have the general time dependent Schrodinger equation, which and whenever I write an equation like this in terms of psi, this h is an operator. In both cases, h is an operator. So for example, for a particle moving in a potential V, h would be minus h cross squared by 2m del squared plus V equal to h, the operator h. Okay, and this acts on psi, so h psi would be this. Okay, so that would be the left hand side of this equation, and you equate that to E psi, and then you solve by imposing some boundary conditions. We will look at a couple of examples, and the method will become clear. Now, somebody asked a very good question saying, in the de Broglie picture, we imposed this condition. Okay, for, or in more precisely, this is what we wrote. Minus I 2 pi nu psi. This was for eigenfunctions. So in the last class, I said that Schrodinger looked at this equation and he wrote nu as E by h, and then he wrote E as capital H by h, and he said the general equation is, yeah, nu as E by h, and h as capital E as capital H by h, and then he wrote the general equation as this. That was not, honestly, that was not a very clear way of my explaining how you go from here to here. Let me now spend maybe a minute trying to explain that. So the idea is the following. Let us say you have an eigenfunction phi1, which has an energy E1, then that, according to de Broglie, satisfies this equation, right? D psi by dt equal to minus I 2 pi E by h, E1 by h, say phi1, phi1. Now d phi2, if it has an energy E2, would satisfy phi2 and so on. Now you consider a general psi, which is some A1 phi1 plus A2 phi2 plus so on, which is a linear combination of these phi's, which is what the principle of superposition says. Then if you just take del psi by del t, okay, what you now get is A1 times del phi by del t, which will be minus I 2 pi E1 by h phi1 plus so on. If you just write down all the terms like A2 times minus I 2 pi E2 by h phi2 and so on, you just get del psi by del t equal to minus I 2 pi by h, that part won't change, times E1 times A151 plus E2 times A252 plus so on, right? Now, this is nothing but minus I 2 pi by h, the operator h acting on A151 plus A252 plus so on. Why? Because h is a linear operator. You can act h on each of these terms, h times phi 1, h times phi 2, etc., etc. And we know that from this eigenvalue equation here, phi 1 has an energy E1. What that means is h1, h phi 1 is E1 phi 1. So the action of this operator on the wave function, so that gives you del psi by del t equal to minus I 2 pi by h, h acting on psi. Therefore, I h cross del psi by del t equal to h psi. Does that explain? I forget who asked. I think Prasenjit asked. Does that explain how the general Schrodinger's equation comes about?
Yes.
Yeah. So we we use the property that h is a linear operator to go from the eigenvalue equation to the general time dependent equation. So any psi in the Hilbert space, any psi in this vector space should now satisfy this equation. That's what we mean. Because if you have a complete set of basis vectors phi 1, and we know from matrix theory that if you have a Hermitian operator, the eigenvectors of that Hermitian operator will be both orthogonal and complete. It defines an entire vector space. So that is the idea. All right. Any questions on this? Now we will go into the interpretation of this wave function. So we now have the Schrodinger's equation, interpretation of psi, which is a function of q1 to qf times t. So how do you interpret this? So the interpretation was actually given by Max Born. By the way, Max Born was a visiting faculty at IISc long back. So Max Born does have an IISc connection. This was in the post or during the Second World War, in fact, when he had to flee Germany. He was temporarily in India before he went to the US. So the interpretation of psi is not too different from what de Broglie had thought about, but de Broglie's interpretation was tied down to three-dimensional space and time. Therefore, taking the mod squared of this psi and integrating it over all volume and multiplying it by some dimensional parameter was equated to the mass of the system, the total mass of the system or the total charge of the system, etc. What Max Born saw in that interpretation, but when extended to the Schrodinger's equation, no longer you can think of it as some sort of a density, because real densities, etc., etc., are defined with respect only to the three-dimensional space. So now it has to be some generalized density which should be extended not just to the three-dimensional space, but to what is called the configuration space, which is the space of all coordinates, all generalized coordinates. These q1s to q1 to qf are generalized coordinates, and the space that they span is called the configuration space. So this was what Max Born noticed, and from there the interpretation became quite straightforward, that mod psi squared, okay, mod psi squared times the volume element in the configuration space is the probability that the system of particles has the configuration in the range of, in the range Q1 to QF to Q1 plus DQ1, Q2 plus DQ2, QF plus DQF. Okay, that is, the particle is in a delta neighborhood of the point Q1 to QF. Okay, and this is the probability. Therefore, mod psi squared is the probability density. Okay, so this is the probability density of the system, that it has the coordinate values given by Q1 to QF. So this was the interpretation which followed from what de Broglie had, but added a slightly additional uh, piece of information to it. Now, de Broglie's wave function had to be multiplied by a dimensional parameter, and that had to be equated to, say, the, if there are n particles each of mass m, then that had to be equated to n times m. In the case of Schrodinger's wave function, there is no such need, because the fact that you consider f degrees of freedom already incorporates the total number of particles there are. But then what is this probability density of? It is the probability density that particle 1 has coordinate q1, particle 2. It's like a joint probability density of all the f particles ha having those f coordinates. Okay, well, f need not be the total number of particles. F could be 3 times the number of particles, in which case this gives you the probability that the particle 1 has coordinates x1, y1, z1, particle 2 has coordinates x2, y2, z2, and so on and so forth. Okay, so that is the meaning of the Schrodinger's wave function. Now let us look at how to set up the problem. So what is the recipe? I discussed this last time. Recipe for solving a problem in quantum mechanics. So now we will not use vague terms like quantum theoretic, etc., etc. Once Schrodinger finished writing the Schrodinger's equation, the field of quantum mechanics is now fully formed, and we will use the term quantum mechanics henceforth. Okay, why? Because we now have an equation of motion for the wave function. Okay, so what recipe for solving a problem? You first set up the classical problem. Classical problem to be set up. Now, what do we mean by the classic problem set up? Usual stuff. You write the Lagrangian, then you calculate the momenta. So Lagrangian is a function of q1s and qi's and qi dots and time. Momenta, you define pi as delta L by delta qi dot. And then you invert this relation to find qi as a function of the momenta. And then you write the Hamiltonian. And the Hamiltonian is defined as summed over all I, pi qi dot minus L, where in terms of qi dot, sorry, this is qi dot in as a function of p1 to pf. You substitute these equations here as well as into the Lagrangian, and then you get a Hamiltonian. So for example, let us quickly do this. Let me then finish the recipe. Then the second step is quantizing. In the Heisenberg picture, the quantization is imposing the commutation relation. We saw that already. Whereas in the Schrodinger picture, quantization essentially means writing pi equal to minus I h cross del by del qi. This is what quantization is. And then equation of motion for psi would be I h cross del psi by del t equal to h, which is now a function, the Hamiltonian, written in terms of q1, q2, so on to qf, And in place of the PIs, you now write this. So on, acting on psi. Okay, so this is the Schrodinger's equation, the time dependent one. So to solve this, solve for H phi equal to E phi, and any general psi is now a function of I equal to 1 to whatever. In general, there are infinite such energy eigenvectors, and it will be some A1 AI times phi I, which is a superposition of these infinite dimensional basis vector space. Okay, this is so solving the basis vectors is what we usually mean by solving a problem. Solving for this eigenvalue equation is what we mean by solving a problem. So let us now consider the particle in a box. Okay, then in this problem, v equal to 0 in this space, v equal to infinity in this space, between 0 and L it is 0. Therefore, minus, so classically the half m x dot squared is the Lagrangian. Then the momentum would be mx dot. Therefore, the Hamiltonian will be trivially p squared by 2m. Okay. Therefore, minus I h cross. So now from this, we go to the Schrodinger's equation, which is h phi equal to E phi. This is what we want to solve. Therefore, minus I h cross del by del x phi. Okay. This whole square divided by 2m equal to E phi. Therefore, minus I h cross, sorry, minus h cross squared by 2m del squared phi by del x squared equal to E phi. All right. Therefore, del squared phi by del x squared plus 2me by h cross squared phi equal to 0. So this is of the form del squared phi by, after this is just solving differential equations, plus k squared phi equal to 0. And we impose the boundary conditions, phi of 0 equal to 0, phi of L equal to 0. That now gives you a discrete set of Ks, which is what the quantization is, which gives you the energy eigenvalues. Okay, so you now have Kn is n pi x by L. These are the only possible solutions, and phi would then be proportional to sine n pi x by L. Okay, and now these are basis vectors. So what we usually do is a normalization. So we say this is equal to some an times sine n pi x by L. And we want, since we now have a very nice interpretation that this is a probability density, probabilities come with the very nice property that integral mod phi squared dx has to be equal to 1. Therefore, that gives you mod an squared sine squared n pi x by L dx going from 0 to L is 1. Therefore, mod an squared times sine squared n pi x by L is just 1 minus cos 2n pi x by L by 2. So it's 1 minus cos 2n pi x by L by 2 integral from 0 to L equal to, this is equal to 1. But this here, this function gives you a 0 because it is a full wavelength. Therefore, this term doesn't contribute anything to the integral. Only this one is non-zero. Therefore, mod an squared times L by 2 is 1. Therefore, mod an squared is just 2 by L. And if you take an to be real, then an will be just square root of 2 by L. Therefore, the basis functions for this problem are square root of 2 by L sine n pi x by L. Now, what is the energy? What are the energy eigenvalues? What are the energy eigenvalues for this? You just write minus h cross squared by 2m. Okay. See, you take this quantity 2me by h cross squared. Sorry, let us write 2men by h cross squared will be kn squared. That is how we wrote, right? From this we wrote k squared. So we now have kn squared, and kn squared is n square pi square by L squared. Therefore, the energy, the nth energy level will now be n squared pi squared h cross squared by 2m L squared. And if you note that 2 pi h cross is h, you get n squared h squared by 8m L squared. You multiply by 4 on the denominator and numerator, and you get En is 8m L squared. Now this is for the simple particle in a box problem. These are the energy eigenvalues and energy eigenvectors. Okay, so these are the energy eigenvectors. When I say vectors, I am using functions and vectors interchangeably. These are the energy values. Okay, so these are the eigenfunctions and eigenvalues. Okay, and any general psi. Okay, any general psi will now be summation over I, some ai coefficient, some constant coefficients ai times psi I. Well, these coefficients need not be constant. Sorry, phi I. They can depend on time. Okay. Now, this is, now let us see this simple. Let us now consider time evolution, since we are anyway discussing this. So let us now consider time evolution, because this was just the time independent Schrodinger equation that we solved. Let us consider the time evolution of the phi's. We know that h phi I is ei phi I. This is true for all energy eigenfunctions, right? Now, this is also equal to h delta phi by del t is h phi I, which will be ei phi I. Therefore, d phi I by dt, or del phi I by dt, let us write it. It's not d phi I, it's del phi I by del t equal to minus I h cross ei, sorry, minus I h cross ei, sorry, minus I e by h cross, minus I e I by h cross times phi I. And this can be integrated very easily. So what you now get is phi I, okay, delta phi I by phi I equal to minus I e I by h cross dt. Okay, you write it like this, and then you integrate from phi I of 0 to phi I of t and time from 0 to t. So what you now get is this is d phi by phi integral. And what do you get? Integral of d phi by phi is basically log phi. Okay. So ln, it's natural log phi I of t by phi I of 0, this is what you get, equal to minus I ei by h cross t minus 0, which is just t. Therefore, phi I of t by phi I of 0, so I'm going to take the phi I of 0 to the other side, exponential of minus I ei t by h cross. Therefore, phi I of t, if you have a particular vector, the eigenvector at time 0 is phi I of 0, then the eigenvector of time t is nothing but phi I of 0 multiplied by this complex phase. Okay. So this is a very important property. So usually in general, if psi, okay, if psi of 0 is an initial vector which is given by a1 phi 1 of 0 plus a2 phi 2 of 0, where all these coefficients are constants, these are constants which don't depend on time, then psi of t can be very trivially written as a1 e to the power of I e1 t by h cross phi 1 of 0 plus a2 e to the power of minus I e2 t by h cross phi 2 of 0 plus so on. All right. In general, in general, this is only possible when a1s are constants. You could have a more complicated scenario where the a1s are not constants, in which case you have to, this becomes a simple maths problem of solving a differential equation, and there are techniques that people have developed for solving this. Okay. So this is, for example, let's consider a particular example where h is h naught plus some v of t, where the v is now a time dependent potential. Okay. Then this is the total h. This is h naught plus v of t. How do you solve this problem? So you usually write IH cross del psi by del t equal to H psi. Now, you know, in general, you know H naught. So let me give you a concrete example of what this is. Let us say you have H naught is, let us say, hydrogen atom. Okay. What do we mean by H naught is the hydrogen atom? It's the Hamiltonian of the hydrogen atom. Hamiltonian of the hydrogen atom. So what is H naught? H naught is minus h cross squared by 2m, the gradient squared, minus e squared by r, where r is the radial vector, the radius of the point, the magnitude. Okay, r is mod of r bar, and gradient squared can be written now. This is just the Laplacian, and you have to write it in spherical polar coordinates. So now you have the Hamiltonian H naught, and we know H naught we can solve for H naught phi I equal to EI phi I, and that basically solves the hydrogen atom problem. Now what we are interested in is, let us say we have the hydrogen atom, but we are applying now an additional light field from outside, and we know that light is an electromagnetic field which is an oscillating electromagnetic field, right? It's an EM wave. So when you shine light on the atom, we are in principle applying a time varying potential. Now we want to solve this problem. Now what do we mean by solve this problem? Given a psi of 0, given some initial state, given some initial state at t equal to 0, what is psi of t? This is the general problem that we are interested in quantum mechanics. In classical mechanics, we are interested in, given a set of initial conditions for the coordinates and velocities, knowing the force, where does the particle or where do the particles land up with what velocities at a certain amount of time. This is the problem in classical physics. In quantum physics, we have translated the time evolution into the wave function. Okay, the wave function evolves according to this Schrodinger's equation. So given a set of initial conditions, and it's a first order differential equation, right? So if you have psi of 0, you can compute psi of t. Any first order differential equation, you can solve it using just an initial value. If you specify psi at any given time instant, you can in principle solve this equation. But what I want to highlight is that this is not always a very trivial thing to do. Okay, we won't be, this is just for you to know that solving a general time dependent equation here is not going to be super easy. All right, so far we have any questions on this? We will touch upon this probably in the next class briefly, but this is important to know that in your context at your level, solving the Schrodinger equation means solving for this. But in general, this solving the Schrodinger equation means this. If you are given a psi of 0, what is psi of t? For a general Hamiltonian, which is h naught plus vt, where we know the solutions of h naught, but we don't know the solutions of h naught plus vt. That's what we are trying to find. Okay. So this is the statement of the problem in quantum mechanics. What is quantum mechanics trying to, what is the information that you get in quantum mechanics? This is what you get in quantum mechanics. Then what? Once you know psi of t, what do you do? So here comes another aspect, an important aspect of the connection between quantum mechanics and the values of classical variables that we define for each system. Remember that you and I are classical beings in the sense when we say that the energy of the system is this. What do we mean by that statement? It means that I have some method in which I measure the energy. Okay. I have a method of measuring the energy, and that energy, okay, I have a method of measuring the energy, and the energy that I measure in the experiment is what I want quantum mechanics to predict. So how does the theory then reconcile and agree with experimental observations? That requires you to do some interpretation. For example, I said quite casually that a general wave function is usually written as so on plus some a n phi n, and the sequence keeps, the series goes on, where phi I are the energy eigenfunctions okay, phi I are the energy eigenfunctions of the Hamiltonian of, let's say, h phi I equal to ei phi I. This is the equation that the phi I satisfy. And I'm telling you that psi is a general superposition of these. What do these coefficients mean? Okay. Now, for psi to be a probability density, sorry, there was a question, I think. Which of these is or are relevant papers to read after today's class, of course, for more insight? Oh, well, uh, I would not suggest reading those right now. Not after today's class, but after the semester is over. You can read them during the break. All right. So what is the meaning of these AIs? Now, whenever one very important thing is before you interpret, this, for example, yeah, when you write psi as a superposition of these phi's, we assume that phi i's are orthonormal. What do we mean by orthonormal? Firstly, they are orthogonal. That is phi j star of times phi I dx or d cubed x, depending on, or it should not be d cubed x. In fact, it should be d sorry dx1 to dxf. The full set of this product, okay, should be equal to delta ij. Why? That is what we mean by they are orthonormal. Okay, so they have been normalized and they are orthogonal. Orthogonal means the dot product. So the inner product is defined as integral of phi I star phi j dx1 to dxf for the vectors phi I and phi j. Now remember to put this star, okay? That's very important because these are complex vectors in general, complex functions in general. So you have to include the conjugate. Okay. Now these are functions. Phi I and phi j are functions. So you have to include the conjugate. And this in general, you can define the inner product for any two vectors. Let us say psi and chi are two functions. Now psi is one superposition of the phi i's because the phi i's are our orthogonal basis. Chi is another superposition of the same phi i's. Now you can define the inner product of these two, and in general that is not zero. The dot product of any two vectors is not zero. Only the dot product of the basis vectors, the I cap and j cap and k cap, the dot products of those three, the mutual pairs will be zero. But any two vectors can have a finite dot product, and that dot product, that inner product, is defined as it's represented. So this is a notation thanks to Dirac. Now we have in this entire discussion, we have somehow, for some strange reason, we did not really mention much of this amazing mathematical physicist who, Schrodinger, of course, brought a great amount of clarity to what Heisenberg did out of pure instinct. But it was Dirac who tied everything together and took the field forward. So what Dirac did was he independently worked out the entire structure of the mathematical structure of quantum mechanics, which Schrodinger and Heisenberg approached from two different directions, and he gave a consistent recipe. So the recipe that I gave you earlier, I said recipe for solving a problem in quantum mechanics. This is in fact Dirac's recipe. Okay, this is Dirac's recipe for solving a problem in quantum mechanics. He was the one who gave this recipe, and of course he did a lot of other things. For example, he was the first one to consider the problem of interaction with light and tried to, and he was the originator of the subject of quantum theory of radiation, which eventually became what is called quantum electrodynamics. And he was the first one to also discuss the relativistic extensions of quantum mechanics, the famous Dirac equation that he came up with almost 3-4 years after quantum mechanics was formulated by Schrodinger in 1926. Dirac around 19, you know, almost by 1927, he had already started thinking about the relativistic extensions. Schrodinger did not really consider the relativistic theory because we'll see what we mean by that when we discuss relativity starting next week. Okay, so it was Paul Dirac who introduced this notation where he wanted to have a notation which worked both for functions and vectors equally. So he introduced this symbol called a ket, which represented a vector, and this here he called a bra. He basically took the word bracket, which we are all familiar with, and he divided it into two parts. A bracket is usually like this, and he said, okay, I'll divide it into two. I'll call this the bra, I'll call this the ket. The ket stands for the vector. The bra stands for the dual vector, which is the Hermitian conjugate of that. Okay, so if you take a column vector, say x1 to xn, this is the vector, let us say x. Then the vector x1 star to xn star would be the bra x. Okay, is that clear? And if you now take the product of these two, you can, in matrix notation, this product is quite trivial. That is nothing but x1 squared mod x1 squared plus mod x2 squared plus so on up to mod xn squared. Okay, and in Dirac's notation, this is simply written as mod xx. Okay, so a vector psi is now written as ket psi like this, and a vector chi is written as a ket chi like this, and this vector psi could be some summation over ai phi I, where this phi I is now a basis vector, and this chi here can be a summation over bi phi I, where phi I is the same basis. And now you can define chi psi, which in function notation would be integral chi star psi dv, where I'll call it dfv, where f is over all degrees of freedom. Okay, which would nothing but in vector notation that would just be summation over, I bi star ai. Okay, so this is the integration that Dirac did. Basically, he approached it in abstract symbols, and he defined in terms of wave function, this symbol means this. In terms of matrix, in terms of vectors, this symbol means this. Okay, so vectors and matrices, vectors and matrices are the Heisenberg notation. Operators and functions are the Schrodinger notation. And kets and bras are the Dirac notation. And that's a more abstract notation. Okay, so we'll be using the ket bra notation because that's a much more uh, user friendly notation without integral symbols and everything. And but of course one has to have a mapping of how to actually do the calculations using this method. Okay, so we now have any inner product defined as this. And we usually normalize a vector as this. Okay, we usually normalize a vector in the Hilbert space as psi equal to 1. What that means essentially, it's a restatement. If you think about this, if you interpret it in the Schrodinger language, that becomes integral over all uh, configuration space psi star psi equal to 1, which is nothing but integral over all dfv mod psi squared equal to 1, which is nothing but Bond's probability interpretation for mod psi squared. This is the fundamental theorem of probability, that all probabilities have to add up to 1. Right? In Dirac notation, we usually say psi is 1, which means that the vector psi is a normalized vector. So psi is normalized. That is the terminology that we use. Okay. Now, if A is an operator acting on a vector psi, this could be the vector, let us say chi. Okay. A could be any operator. Then chi is going to be psi A dagger. Okay. So if chi is A psi, then chi is this, is psi A dagger. This is the Hermitian conjugate. Think in terms of matrices. If you have a column vector, then the corresponding, if you have a square matrix acting on a column vector, let's say this is n by n, this is n, then this is let us say some column vector. This is x1 to xn, and this is a11 to a1n, then an1 to ann, and this is y1 to yn. Okay, then this vector here, y1 star to yn star, which would be, this is, let us say we call it chi, then this would be the bra chi, that you can easily show is nothing but x1 star to xn star a11 a1n, and this an1 to ann, the entire dagger. Dagger, this symbol dagger means you take a star and then you transpose. That is what the symbol dagger means. It's called the Hermitian conjugate. This is just a simple complex conjugate. This is the Hermitian conjugate. This is a simple complex conjugate, and this means transpose. Okay, so the conjugate transpose of a matrix, when you want to take the conjugate of a matrix, you just take the complex conjugate of every element and then you do a transpose of it. That makes it a Hermitian conjugate. Now, since all of you are familiar with matrix theory, in general, if you have a vector psi such that psi is 1, okay, psi is a normalized vector. If you operate any A on it and you get another chi, in general, chi is not equal to 1. If psi is normalized for any A, any operator A, chi equal to A psi need not be normalized. So one has to do a normalization afterwards. All right. But if A dagger A is just the identity operator, then chi will be equal to psi, right? If you look at this equation here, sorry, I did not write this fully. So chi is nothing but psi a dagger a psi. If a dagger a is the identity operator, then chi will be psi, which will be 1. So what this means is, if a dagger a equal to the identity operator, then whatever vector, if the initial vector psi that this operator a acts on, if this vector is normalized, then a psi is also normalized. If if psi is normalized, then a psi is also normalized. So such a vector, this property a dagger a equal to identity is called unitarity. Okay, and a vector a that satisfies this property is called a unitary, sorry, not a vector, an operator a which satisfies this property is called a unitary operator or a unitary transformation. Okay, that's a unitary transformation. Now, we are particularly interested in unitary transformations in quantum mechanics because according to the interpretation, the probabilistic interpretation, every physical state described by a wave function in quantum mechanics, let me write this statement, in quantum mechanics, every, okay, state described by a wave function, sorry, every state described by a wave function has to satisfy the probability normalization condition. That is, if you have the if you have the wave function psi, now I'm going to use the term wave function, but I'm going to represent it as this abstract ket. Psi has to be 1 in quantum mechanics. Okay, so any transformation that we think of this psi, which takes it into another physically probable vector, meaning that if psi has to go to say some a times psi, which is equal to some vector chi, and if this chi has to be a physical state, then chi has to be 1. This implies a has to be unitary. Okay, so this unitarity condition, we only consider unitary transformations. We only consider unitary transformations in quantum mechanics, at least to start with. We are only considering unitary transformations for this simple reason that if you want states to be described by wave functions and the wave function has a probabilistic interpretation, then the only possible transformation that connects the two wave functions like that is a unitary transformation. This would be a technically completely correct statement to summarize whatever I discussed in the last few minutes. Okay, so quantum mechanics, that's, you will hear statements like quantum mechanics of wave functions is perfectly unitary. What do we mean by that? This is what we mean, that if two states of a system, or if two states which are representations of physical systems, according to Max Born's interpretation, these states, the wave functions representing these states, have to satisfy the probability normalization to unity, which means that any operator, or if one of the states is a transformation of the other, then that transformation better be unitary. Okay. So that is the idea of. Now in normal vectors, for example, if you have the x and y axis and you have a point here, the length of this radius, this position vector here is preserved. Let us say you take a new set of axes x prime and y prime. The length of this vector is preserved only when the transformation from the old basis xy to the new basis x prime y prime is what is called an orthogonal transformation. Think of, and the length of the vector in quantum mechanics is basically unity. The length of any vector is unity because of the probability interpretation. Every vector that you can consider, every state, every wave function that we consider is going to be normalized according to this rule, which means that any change of basis has to preserve this so-called norm of the vector, the length of the vector, and that has to be a unitary transformation. So in real spaces, it's an orthogonal transformation. In complex spaces, it's a unitary transformation. So unitary and orthogonal are sort of unitary is the complex extension of orthogonal transformation. That's all. Okay. So this is the idea. So we will pause here for today. From the next class, or in the next class, and this Friday we will have a class at 9:30 in the morning. We will discuss more consequences of quantum mechanics, the uncertainty principle, etc. And with that, we will finish the quantum mechanics portion. Starting Monday, we will be going into relativity. And at the end of relativity, here is what I plan to discuss in relativity. The basic framework, Lorentz transformations, and then relativistic dynamics, how energy, momentum, and other things are defined. All that we will discuss. But towards the end, we will also discuss a little bit about general relativity. And if time permits, in a completely non-technical way, the standard model of particle physics, and try to see how relativity is essential for describing the real world we live in. And non-relativistic quantum mechanics a la Schrodinger is not sufficient. This is a huge step, but you really need to go into relativistic physics. And what is meant by relativistic physics? Is it some new kind of physics, or we will see all that next week onwards. Okay, so I'll give a homework on the quantum mechanics portion this week. Once I finish discussing uh, the uncertainty principle in the next class, I'll give you a homework which you can solve. That homework will probably be due 2 weeks from now. And then you have the relativity portion on which I'll give another homework, which will be probably due after the exams or something like that. Okay, so that will be the last two homeworks for this course. And yeah, any questions on what we discussed today? So what we discussed today is how to work with Schrodinger's equation, how to apply it to various problems, what is the recipe for setting up a quantum mechanical problem and solving it, and what is the interpretation. And we also looked at this rather concise notation introduced by Dirac and how to work with that notation. And finally, we ended up at the notion of unitarity, which is a very, very important concept in quantum mechanics. And all the transformations between any two wave functions has to be unitary. If the two wave functions are normalized in the sense of Max Born, that is, they do represent probability densities of physical states, then the transformation connecting them has to be unitary. That is what we meant. All right. If no other questions, then we will wind up today's class and meet on Friday at 9:30.